Okay, thank you, Jing. And good morning, good afternoon, and maybe good evening, everyone. So today my topic will be on the radiator cooling technologies. And basically, our group invented a smart radiator cooling technology for all-season household thermal regulation. And in this talk, I will first introduce the background of developing radiator cooling technologies that is solving the energy challenges in our world. And next, I will briefly introduce the history and the challenges of passive radiator cooling technologies. And finally, I will introduce our work, including the core functional material, the device performance, field tests, and application simulation. So I think the main goal of developing radiator cooling technologies is solving the energy problem in our society. The energy crisis is a significant bottleneck in the supply of energy resources to an economy. The left-hand side shows a picture taken in 1973, which was the first day of gas rationing in California due to energy crisis. From this picture, we can see that the energy crisis not only hampers the development of economy, but also causes great trouble to our daily life. So scientists and engineers have been fighting really hard to seek for solutions to the energy crisis. And the solutions may be sorted into three categories. The first is renewable energy, including solar, wind, etc. And the second is energy storage solutions for renewable energy, that is better batteries. And the third is to reduce the energy consumption, which is straightforward as well. If the society is demanding less energy, the burden imposed on the energy generation will be eased. So this is the data we found from the United States Energy Information Administration. And this is the roadmap of the energy consumption in the United States in 2020. The left-hand side shows the different sources of energy, while the right-hand side shows the end-use sector. That is where the energy went to. Please note that here, the residential and the commercial sectors contributed to roughly 30% of the total energy consumption in the United States. Well, this number didn't include the electrical system energy losses. So if we add them together, it may be more than or even roughly 40%. So the residential and commercial sectors, mostly buildings, are really consuming much energy. And we need to take a closer look at what is taking up so much energy. So this is the household energy consumption in the United States in 2015. And this is the electricity consumption in households. So the temperature regulation, that is heating and cooling of your building, may take up 32% of the total electricity. But please note that in some areas, such as Alaska, some houses does not use electricity or not solely relying on electricity. They may burn fuels or woods to heat up the space. So we need to view it in the energy perspective. So when analyzing it using energies, we can find that the space heating and cooling may contribute to more than 50% of total energy consumption in average households. So that's why we are trying to develop new technologies to save this portion of energy. And one really popular technology is called cool roof technology or radiator cooling. So here I will briefly introduce what is radiator cooling. So let's assume there's a building in summer. So its temperature is really high. And when it faces a clear night sky, which is a natural heat sink with a very low temperature, roughly 3 Kelvin. So by nature, it will radiate heat into that in IR range. And this cooling power can be calculated using this equation. And where the A is the total roof area. And this sigma is the Stephen Boltzmann constant, and epsilon R is the thermal emittance. while the T and the T sky correspond to the temperature of the roof and temperature of the sky. So here, the epsilon r can be calculated using this equation. And we are only calculating in this range from 8 to 13 microns because of the scale window, limited by the transmittance of the atmospheric gases, this range. And what if we have a sun up in the sky? The solar radius will reach the roof, and the roof will absorb part of it. So this can be calculated using this threefold equation, where the solar absorbance is calculated from 0.3 micron to 2.5 microns. So the whole picture is really clear. The solar radiation hits the roof and is partially reflected and partially absorbed. In the meantime, the roof radiates mid-IR light into the outer space. So if we want to achieve radiative cooling, we need to maximize both the solar reflectance and the thermal emittance. This idea was maybe first generated more than half a century ago. And in recent years, it was developed using micro-nano technologies. And this is a paper published in Nature in 2014 from Shanhui Fan Group. And this is a really famous one. So this is a basic idea about radiative cooling. Now I will briefly introduce its history. So surprisingly, radiative cooling is not a new idea. At least the cool roof technology is not new, because long ago, the Greek people were already painting their walls and roofs with white paints. Their idea is to minimize the solar absorbance only. But in the last century, people are trying to use these polymers, paints, or simple film structures to minimize solar absorbance and maximize thermal emittance simultaneously. But their performance were rather limited. And in the recent years, thanks to the fast development of macro and nano technologies, the performance of radiative cooling materials can be further optimized. And in the recent days, the current trend can be sorted into 3 stages. In the first stage is maybe from 2014 and 2016, and the scientists are only developing complicated or dedicated nanostructures for optimal performance. And scalable production was not an option at that time. And afterwards, people are trying to use some advanced technologies to achieve scalable manufacturing. And some groups also trying to make use of structural material like wood to achieve radiative cooling. And nowadays, scientists are trying to make scalable fabricate material for clothing and tents. Now we have already finished the introduction of this technology, but what is the challenge is facing? So this is the United States map, and different colors correspond to different climate zones. For example, in Florida, it's really hot, so it's colored in white. And in Alaska, it's really cold, it's colored in black. And the cool roofs, of course, is really good option for buildings in Florida. But in Alaska, it's really cold. People living there, they may not want that. But what about climate zones with large temperature variations in between? What will happen? So let's use Los Angeles as an example. This is the local climate data of the Los Angeles. So you can see we have highs and lows, and both of them vary with the month. And what is the best roof temperature? So this is a desirable room temperature of 22 Celsius degrees. You can see in sometimes the environmental temperature is higher than that number, in sometimes lower. So if you have a cool roof mounted on your building, when the temperature is high, okay, it works perfect. It decreases cooling energy consumption of your house and thus decreases your energy bills. However, when it's cold, this kind of roof, due to its static performance, it will continue to lose heat into the outer space, so that your heating energy consumption will be increased, so as your bills. And to tackle that problem, our group invented this temperature adaptive radiative coating, or the so-called TARC. So what is TARC? Let me explain it using this figure. This figure, with its horizontal axis as the solar substance and the vertical axis as the thermal emissivity, all materials can be put into this plot. So the normal warm roof, metal roof, and the cool roof can be put into these three corners. So what we invented is our TARC material whose thermal emissivity may be switched on and off passively, automatically, according to environmental temperatures, while its thermal absorbance is optimized in a holistic point of view. And this is the data points of our work. The y-axis is the scale window emittance, and the x is the surface temperature of your roof. So you can see in this figure, the radiative coolers and the metals, both of them have static thermal emittance regardless of surface temperature. But our TARC material can have a small emittance at low temperature and a high emittance at high temperatures, so that it only cools the building down when it's hot. So the core functional material of our technology is called vanadium dioxide. So vanadium dioxide is a fission material, and it is subject to a temperature-driven, reversible, fast, automatic transition from insulating phase to a metallic phase upon heating. And its fission temperature is roughly 67 Celsius degrees. And even though it was discovered in 1959, its mechanism is still in debate. Thankfully, we are not discussing the mechanism in this talk, so I will just briefly introduce what will happen upon phase change. So upon phase change, it will change from a metal to a metal, or from a metal to a dielectric insulator. And our group also used a tungsten material to dope the VO2. With a higher tungsten concentration in VO2, the phase change of this material will be decreased. So in this approach, we can simply calculatedly control its tungsten concentration to tune its phase change temperature to room temperature. And a simple material is not enough. So I also designed the metamaterials pattern so that the phase change will be amplified. So this is our TARC material, and it's mechanically flexible. And this is a photo of that. You can use a tweezer to bend it, and the deformation will not cause trouble. And this is the SEM image. So here is the cross-sectional view of the TARC. It has 3 layers. The top layer is tungsten VO2, and it was patterned by lithography. And this is a barium fluoride dielectric spacer, and this is silver metal back mirror. When the temperature is below phase change temperature, the tungsten VO2 is in its insulating phase. It's a transparent air material. So the whole structure serves as a mirror, and it has a low thermal emittance. And when the temperature is increased, the tungsten VO2 becomes a metal, so that the whole structure turns into a classical super absorber metal material pattern with a high thermal emittance. And this is comes to simulation. You can see at high temperatures, strong plasmonic effects appears, so that the emittance is increased. So this is the device performance characterized by spectrometer and the IFTR. So in this picture, the blue curve and red curve are the I state, low temperature state, and M state, high temperature state, respectively, while the solid curve and the dashed curves are the experimental data and the simulation data. So in the visible to NNR range, the absorbance of solar light is almost static, regardless of the local temperature. Meanwhile, its thermal emittance can be switched on and off according to the temperature. And this can also be verified by an air camera. The air camera is designed by based on Steven Boltzmann law, so it will capture the air power radiated from a remote object for remote temperature measurement. So if you use an air camera to look at a piece of aluminum foil with a small thermal emittance, the readout will be super small, like -40 or something. However, if you use that to measure the temperature of tape with a thermal emittance close to 1, you will accurately get its real temperature. So we use that to measure temperature TARC. When the TARC's temperature is cold, the readout is really small, close to the aluminum foil. When the temperature is high, so its readout is close to tape. That's as with what we expected. And this is a video shows this change. The left-hand side is TARC, the right-hand side is a high emissivity performance. And by increasing the temperature, you can see at first the TARC has a small readout, and finally its IR temperature matches that of a reference. And we also measured the cooling power that using a cryogen-cooled vacuum chamber. We coated the interior surfaces with high emissivity coating to simulate the outer space. And we use aluminum foil for reference. So the result shows that at low temperature, the cooling power TARC is small, and high temperature is really large, and with a fitted emissivity of 0.9, just as the FTR's result gives us. And we also conducted a few tests of TARC in Berkeley on a normal roof. So we also erected a shield to block the sunlight after 2 p.m. so that we can emit the case when the sun is blocked by a piece of cloud. And we measured a total number of 3 different materials: a TARC, a commercial cool roof coating, and a commercial normal coating we see everywhere. So the cool roof coating has small solar absorptance and a large thermal emittance, while the normal roof coating has a high solar absorptance and high thermal emittance simultaneously. And here are the few test results. Let's analyze it from left-hand side to the right-hand side. In midnight, the environmental temperature was really low. So the TARC switches its thermal emittance off so that its temperature, the TARC red curve's temperature, is close to the ambient temperature, which is green, while the 2 roofs are suffering from the overcooling problem. And after sunrise, all temperatures rose, and the normal roof coating with a high solar substance rose more. And the TARC is in between, and this is designed. And after the sun was blocked, all 3 coatings using radiative cooling to decrease its temperature. And after the temperature drops beyond the free chain temperature, you can see the TARC switched off its thermal emittance to conserve heat, this red curve, from this point to this point. So by comparison, our TARC, when it's heated, it can have a comparable performance as that of a commercial white roof coating. And upon cooling, it will switch off its cooling power. So actually, what we invented is the entry-free air conditioning for households, just like this. And now we know TARC sounds good, TARC works good, but how good it is? So we continued our work and use an adiabatic simulation using real climate database to calculate the year-round understreaming of TARC compared to all other materials. So this is the basic physics of that simulation. And this is the result in Berkeley. So with climate database of Berkeley, including the Joule temperature, the cloud, and the wind speed, we can calculate the surface temperature TARC in different months at different times, and calculate the total understreaming of TARC. Similarly, we can calculate any arbitrary material with a combination of solar absorptance and thermal emittance, and compare it with TARC, and plot the result in this 2D figure. So whenever the result is positive, it means that TARC behaves better than this combination alpha, and epsilon. So you can see in Berkeley, TARC outperforms all possible materials in an all-year-round perspective. So by switching the thermal radiation and optimally absorb solar energy, TARC saves more energy than oxygen room materials we integrated all year round in Berkeley. And furthermore, we want to analyze the practical scenario. So all practical material fall in these two sections. So we compare TARC with these materials and plot the results in this figure. This is the United States map. And we did the comparison using the climate database of these major cities. And the red circle means that TARC performs better than all practically possible materials in that city. And the blue curve means that there is at least one material that is better than TARC. So you can see this result is well expected in Arizona and Florida, where the climate is really hot. TARC is not as good as cool roofs. And in Alaska, okay, no cool roof technologies might be used. But in all other areas, TARC works better than all practically possible materials. And another example in Ardimo, and we use a similar method to do the calculation. And we found that if we use an example of a typical single-family building with a roof area of 118 square meters built before 1980, a total energy source saving of TARC may lead to 22 million joules per square meter per year. And so this kind of building may save a total amount of 2.64 gigajoule per year. And assuming that the United States has more than 100 million households, and by rough calculation of the energy saving, and we compared with the total electricity generation in the United States in 2020, we find that the potential energy saving of TARC in the whole United States might equal to 1% of the total electricity generated. This is a great amount of energy. Of course, this estimation is really, really rough, but I think it shows the potential of smart radiative coating that may minimize the overcooling problem of cool roof technologies at night or in the winter. So to wrap the story up, we invented the smart radiative cooling, and it makes use of phase change material, and we use metal materials design to amplify that phase change. And we use the tungsten doping to tune the phase change temperature to room temperature. We achieved a passive smart switching of thermal emittance, and we optimize the solar reflectance in a holistic point of view. And we developed a fabrication technique to achieve mechanical flexibility. And for the future work, I'm now working with my colleagues on the next generation of TARC. First, we are increasing its robustness and lifetime. We are targeting at a 3 years lifetime in the next generation of this technology. And we are also trying really hard to achieve scalable production. And we hope that our next generation of technology will be published soon. So I would like to thank my advisor, Professor Junqiao Wu, for all the advice and the support, and also my co-advisor, Professor Jie Yao, who is an expert in metal materials and metal surfaces. He helped me with the design of this structure. And I would like to thank Dr. Ronan Levinson and Dr. Jeffrey Urban from LBNL, and Professor Ali Javi and Professor Kostak Regulopoulos from UC Berkeley. They helped us with the characterization and the simulation of TARC. And we thank these fundings and organizations and fabrication centers. And finally, I would like to thank Wu Group members. Thanks. And this project can never be achieved without them. So that's all for my presentation. Thank you all for your attention. And yeah, questions are welcome. Thank you.
Thank you, Kaichen.
Thank you.
Yeah, due to the time schedule, we may allow like 2 questions Anyone have a question can raise your hand and I can unmute you to ask the question, or you can type your question in the chat box. Maybe I can begin with a question. It's a good talk that's faced the good timing of the gas price right now. So so I was wondering, like, what is the mechanical strengths? You mentioned it's a flexible, and you mentioned that you are trying to work on to make it more robust. What is the mechanical strengths of this material? We know the roofs are experiencing a lot of extreme conditions. Like we may have raindrops, we have snow. Sometimes we may have some objects to impact on the surface. What is the mechanical strengths? Like, can they resist in those factors in the real?
That's a really good question, and it's a really practical question. So first of all, the fabrication is actually a transfer method. We transferred the tri-layer structure onto a piece of tape, the scotch tape. So for the mechanical strength of this TARC technology, it's actually the mechanical strength of a tape. So I think now it's good. But for the robustness against the weather, I have to admit that these non-structures is not that robust, but we can cover it if it's a piece of PE, polyethylene film, so that it can block all the rains and the dust from this from the outside, so that the lifetime will be increased. Of course, this is not a really perfect solution. So that's why we are developing the next generation TARC to solve this problem once and for all.
Sounds good. I can tell that you probably need some self-cleaning surfaces, outer surfaces.
Yeah.
Sounds
I need
good.
your help with that.
Hopefully, hopefully we will have come up with some good technology.
Yeah, I hope so.
Yeah. Any questions from other audience? If no, we can move on to the next speaker. And thank Kaichen again for your wonderful talk. Oh,
yes,
there's one question from the audience. Oh, he sent a message direct to me. I can unmute you. Let me unmute you. Okay, I can read his question. So he was asking. So this question was from Srinivas. He was asking, like, when it comes to a hurricane, so typhoons, roof structure shape plays a vital role. So do you see any chance of providing kinematic links to the roof so that it can change its angle, thereby adapting to angle of repose of snow when it snows in heavy amounts? Also, flat or slope roofs, like selection based on climates. Another aspect is hemisphere roof, like Moscow hemisphere, which is stronger. So, like, he was asking, like, a different shape of roofs, and can you adapt to it, and also adapt to like different weather? I can send this message to you as well, or everyone in the meeting. Yeah.
Okay, let me read that. Hurricane, typhoons, roof structures shape play better role to see and chance provide kinematic links to roofs so that it can change its angle. Yeah, I think so. So the first point of the answer lies in the mechanical robustness against the hurricanes and typhoons, and the answer is the same to the answer to Jing. And another, the most important thing is whether the TARC structure can be applied to this kind of deformed or strange-shaped roof tiles. Yes, I think so. As we just discussed, it actually has a similar mechanical performance as that of scotch tape. So it can be easily pasted to any roof tiles with any shape. So I think the answer is yes.